wants to hear that. All right. So, once again, last time obviously we started talking about chapter 12, and we started talking about Q. And Q is, like I just was saying there, calculated the same as we do K. So it is the concentration of our products over the concentration of our reactants. Just like what we do with K, we do take the coefficients as the exponents for everybody. Also, if it's a solid or a liquid, we don't include it in Q as well. And really, the purpose of Q, or one of the sort of main reasons why we would solve for Q, as we talked about last time, is just a basic question of you're given all the concentrations, maybe you're even given all the pressures, and you want to know, are you at equilibrium at that point? And that's what Q will help you know if you are at equilibrium. The second thing that Q will also help you understand is if you are not at equilibrium, which way does that reaction need to proceed to eventually reach equilibrium? So do you have to make more products to do that? Do you need to make more reactants? And you can do that by comparing the Q value to the K value. And if the Q value is larger than the K value, it means you're not at equilibrium. And in order to reach equilibrium, you actually need to go opposite of where that little thing's pointing. So towards the reactant side is basically where you need to be. If you do calculate Q and it does equal the equilibrium constant, then you don't have much of a problem probably at that point, but you are at equilibrium. And if you calculate Q and it's less than K, once again, you're not at equilibrium. And in order to reach equilibrium, again, you got to go opposite of where that's sort of pointing. So towards the product side needs to be made, or more products need to be made to reach equilibrium. So as we did one last time, kind of just a basic Q problem would be that type of question. Are you at equilibrium? If not, which way you need to go to reach equilibrium? Remember that because you calculate Q the same way as you calculate K, the only way that you can calculate Q is you have to be given pretty much everybody's concentrations in a sense, or everybody's pressures. Otherwise, you have no way to calculate Q. So where this can also come up is what we also talked about towards the end, which is ice tables and doing equilibrium calculations. So again, if you get to sort of an equilibrium calculation when you are given all of the values there, you should really calculate Q just to make sure you're not at equilibrium, which probably is the case, but also to make sure which way the reaction is proceeding so that you could do the calculation correctly. Thank you. So speaking of that, that is how we solve for equilibrium concentration. So if we had an equation such as this, and everybody there we'll just say is a gas, we would set up an ice table. And when we do an ice table, as we talked about, ICE, I is initial. So in the case of the situation here, it could be initial concentrations, which should be molarity. It could also be initial pressures if you're dealing with a KP sort of value as well. Once again, the pressures do need to be in atmosphere so that everything, again, works out correctly. You would do your initial concentration. So again, if we had, say, 4 molar, and they really didn't tell you anything about the product side, for example, which is common sometimes. You can safely assume, like we did in a couple of those examples, that you really have nothing going on initially on the product side, that it's 0. That also helps you really sort of decide which way this reaction is going, because clearly if you have nothing on the product side, then it's got to head towards the product side because all you got is reactants, which would kick off the forward reaction. Remember, the change part here of the ice table is really the important part of it. That's ultimately what we're trying to sort of solve for. And since we know the reaction is going to the right on the reactant side, these guys should be minuses as they're decreasing with time. We also, as we talked about, really important, you do need to take the coefficient into account when you do this. And this would be something like minus 2x, and x really represents the change that's happening there. Again, the 2 there takes care of all the kind of mole-to-mole relationship, all that stoichiometry stuff that nobody really wants to think about, right? So it kind of does all that for you when you put the coefficient in there. Here we got our minus 2x, and here we don't really have a coefficient, but it is a product, so it should be increasing with time, and you would have a plus x on that side. And then pretty much what we would do, obviously, is for our equilibrium line is just simply carry down everything. So whatever you got going on there, you're basically just going to kind of carry it down. And at this point, it really is sort of a math problem. The goal here is to solve for what X is, and we do that by using our equilibrium expression. Again, our products over our reactants. And obviously, in a case like this, you would be given a K value. I'll just go 10. And you would be given that K value in this case. At this point, you would pop pretty much everything in the equilibrium line into your expression, and you would solve for X. And really, we talked about a couple different ways that that's probably going to play out for you in terms of solving for it. For example, you can use the quadratic. And again, that is something like ax squared plus bx plus c is equal to 0, where x is equal to minus b plus or minus the square root b squared minus 4ac divided by 2a. As we talked about, as we saw in an example last time, again, you will yield two x values in this case, and one of those x values will not make sense. So when you do get your x values, they are every single x in this table. And basically, the one that will not make sense in this case is whichever one you put back in, that basically will yield you usually a negative concentration. So as we talked about last time, it may not necessarily be the actual value being negative that's the wrong thing there. Again, you could have two positive x values as well, but it's when you put it back into that equilibrium line, if you do end up with a negative number, which obviously you cannot have a negative concentration or even a negative pressure as well, then that's clearly the one you shouldn't use. You should use the other one. We also could have a situation like we did in one of the examples there where it is a perfect square, for example, on both sides. And you could just kind of square root both sides. I think some of you maybe also on that one did the quadratic, which also demonstrates, again, that you could always roll that way and you should get the same answer. But also you should also look maybe for an easier way if there is an easier way, but you could definitely roll through it. Remember that once you get the X value, you're just going to pop them in here. And again, those are going to give you your equilibrium concentrations in this particular example. And remember, since it is math, when you're done, you could kind of check to make sure, hopefully you didn't make a mistake. And that is, once you have the equilibrium concentrations, you can actually put it back into this expression. And obviously, it should be pretty much in the ballpark of what your K value was. Again, it may be slightly off with rounding, but it should definitely be in the ballpark. So for example, if I solve for everybody at equilibrium, I put it back into this expression, and again, I get a K value that's like 90, that's clearly way off the 10. So something probably went wrong. But again, if I put it back in, you got like 10.1 or 9.9 something, you're going to be pretty close to that value again. Might be slightly off with rounding. Any questions on any of that stuff we talked about? Yeah. Again, it really is when you do the quadratic and get those two x values. It's basically what happens when you put them back into the equilibrium line. And one of those values in the equilibrium line are multiple values in the equilibrium line. Once you put the x back in, will yield you a negative number. And again, you can't have a negative number in terms of concentration or pressure. Other question? No. And that's an important thing to remember for later chapters. You can't have a negative number at the end there. Yeah. So there's a lot of times people end up with negative numbers because it's like they just roll an autopilot and go like, I'm supposed to do this. But think about that as you go through it. You can't have, a negative concentration or pressure at the end in pretty much all cases. Other questions on that? All right, then we left off with this example, which clearly you worked out at home. Maybe, we'll see. All right, if not, we're going to work it out together here just to see if we remember math. Between all of us, we should hopefully figure it out, I hope, right? All right, so we're going to look at this one, which is the initial concentrations of H2I2HI are 0.00623, 0.00414 molar, and 0.0224 molar, respectively. Calculate the concentrations of each of these guys at equilibrium. We have pretty much the same reaction we were looking at earlier, which is 54.3 is the K value. In this particular case, if you did it or if you did not do it, this is one of those cases where if you look at what was given to you, you have the concentration of everybody here. which means really in this case, this is really the second place where you really should calculate Q just to make sure you're not at equilibrium. My guess is you would not be, otherwise it wouldn't be much of a problem. But more importantly, to know which way the reaction needs to kind of proceed to reach equilibrium. So this would be a case where we would want to calculate Q. And Q in this case would again be the concentration of HI, and we're going to square it. Again, we do Q exactly the way that we do K. So divided by the concentration of H2 divided by I2. And in this case, we're going to put our initial concentrations in. So we got up on top there 0.0224 squared divided by, we'll go 0.00623 and 0.00414. So again, we're going to calculate Q here. And we will get 0.0224. We're going to do a squaring of that, going to hit equals, divided by 0.00623, going to hit equals, divided by 0.00414. And that looks like a 19.5 as my Q value in this particular case. That means in this particular case, Q is less than, equal to, or greater than K. Yes, it is in this case. So K is 54.3 and our Q is 19.5. That tells us really two important things as we go forth in this calculation. It tells us, first off, we're not at equilibrium, which probably could guess. Otherwise, like I said, not much of a problem at this point. But more importantly, it tells us which way this needs to go to reach equilibrium and which way does it need to go to reach equilibrium. Towards the product side, yeah. So this is going to actually flow the way we probably imagine. And if you didn't calculate Q in this problem, you lucked out because it's not going in the other direction. So you happen to get lucky in case you didn't do that. But this means that, like normal, our change part is really what would be affected, as we talked about last time. So again, here, if you got a Q that says it's heading in the other direction, our reactants would actually be increasing, our products would be decreasing. But in this case, we are going towards the product side. So our reactants are decreasing, which should be minuses, and our products should be pluses. So good for you if you did it, or good for you if you skipped it and you got lucky, I suppose. Either one of those two you could take. So we're ready to sort of do our problem here. So we'll do our, rewrite my equation here, a little H2 plus I2 going to our 2HI. We can do our equilibrium expression, which is pretty much the same as our Q we just did there. HI squared divided by H2 concentration and I2 concentration. And what do we got there? 54.3, I think, was the constant. So initially here, we are going to put in our values. So for H2, we had 0.00623. For our I2, 0.00414. And for our HI, in this case, we actually do have a value, right? So this is not zero here. We were given an initial concentration of this. So you don't want to go again on autopilot here and just zero out that side, right? So we do have an initial concentration of that. Any questions on that so far? All right, so change part here, we're going to do minus x, which we know for sure since we did our Q, minus x, and that's going to be a plus 2x. Also, a very common mistake people make is they're so used to minusing those things, they do a minus instead of plus on that side. So again, it is a plus on the right-hand side. So we will end up with, at equilibrium, 0.00623 minus x, 0.00414 minus x, and 0.0224 plus 2x. Any questions on the table here? All right, at this point, we got a lot of stuff here. So we're going to put this into our equilibrium expression, which is going to give us 0.0. Put an extra zero there. That would not be good. There we go. All right, 0.0224 plus 2x, that's going to be squared. divided by 0.00623 minus x times 0.00414 minus x, and that is going to equal 54.3. So we got a lot of stuff to factor out here, right? So I'm going to kind of do it maybe top first and then bottom, and then maybe put them back together correctly just to keep track of everything. So I'm going to basically do this guy. So we'll do the top here and see what we end up with. We got 0.0224 plus 2x, and we're going to do that twice right there. So that should get you here. 0.0224 times 0.0224. And it's going to get you something like, we'll go with 5.01. I'll do a little scientific notation so I don't have too many zeros lurking around. We're going then do plus 0.0224 times 2x. And that's going to give me basically 0.0448x. We will also have another 0.0448x, and finally a 4x squared. And again, hopefully we know how to do that. Yes, in and out. Yeah, sounds really good right about now, but we'll do that later maybe. Yeah, so we'll combine everything up here, and we got a 4x squared. We'll combine our x's there, so that's basically 0.0448, two of them there, so it's going to get us 0.0896x, and then we got a plus 5.018 times 10 to the minus 4. So that's basically what you get if you work out the top part. Any questions on that there? All right, we're going to do the same thing for the bottom. I think I'm going to flip the page and do it cleanly up here, so hopefully I don't mess it up. We'll go a different color just to keep it fresh. All right, so here we have, in this case, 0.00623. And that was minus x, and what we got there? 0.00414 minus x. Again, same deal on this. We're going to kind of go in and out on that and distribute everything. So that gives us 0.00623 times 0.00414. Again, I'll do a little scientific notation on that guy there. It's kind of a big number there. 2.579 times 10 to the minus 5. We then will have minus 0.00623x minus 0.00414x, and that's going to give us a plus x squared once again, kind of in and out to both of them. We're going to combine everybody here, so that's going to give me an x squared, 0.00623 plus 0.00414, going to get me a minus 0.0104x, and what we got left there, plus 2.579 times 10 to the minus 5. And again, that obviously is the bottom part. Any questions on that math there? No. All right, now we could kind of put it back together, put the top on the top, the bottom on the bottom. So we'll go with essentially, I'll put a little line here. Pop them back together here. That way. All right, so do maybe a little rounding here. 4x squared, basically on top, plus 0.0896x, plus, what do we have there? Well, I'll turn decimal, 0.000502. Divided by what we got on the bottom there, x squared minus 0.0104x plus 2.58, I'll do a little rounding there, times 10 to the minus 5, and that's going to equal our 54.3 at this point. All right, so everything on the bottom now, We haven't done enough multiplication. We're going to multiply right to the other side there and get everybody on opposite sides. So that gives us up on top, nothing changing. And again, we're just going to basically multiply everybody on the other side by 54.3. So 54.3x squared minus 0.565x uh, plus 1.40 times 10 to the minus 3. At this point, we could just combine everybody to one side. I'm going to move everybody on this side over here because that'll just give me a positive x squared. You don't necessarily have to, but I'll just keep the x squared part positive. And if I do that, I'm going to end up with 50.3x squared minus 0.655x plus 8.98 times 10 to the minus 4 is equal to 0. And if I didn't screw that up there, there's a good chance that I didn't, hopefully. That is an A, B, and C happening in this case. Any questions up to there? Yeah. Yeah. You need to show something. I just showed every step so you could see the entire thing and where everything came from. But you got to show something. You can't just show an answer at the end. So you got to show some type of factoring and something, like this perhaps along the way. And so, yeah, so you don't necessarily have to do every kind of in and out. But again, I just did that so you could see where all the numbers came from. Yeah. Other questions? But it cannot just be the end number that was punched into your calculator for your own good, because if you punch into your calculator wrong, you get no points because you have no work. Yeah. So you got to show something. Yeah. We clear on that? Yes. Okay. All right. So at this point, x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. I'm going to get me a fresh page, I think, on the other page here. So that's going to give me x is equal to our minus b in this case, which actually turns that into a positive, I think, 0.655 plus or minus. And again, I'm just going to kind of do all the square root part inside here. So that's going to be b squared, 0.655 basically squared, minus 4 times a, which is 50.3 times c. That's what I'm supposed to go with. Minus 4 there, I hope. And that's going to get you, I believe, something in the square root here of 0.248347, which if you then take the square root of it, it'll get you 0.4983. That's going to be divided by 2 times a, which is 2 times 50.3. And that's about 100.6. Again, this is going to give us our 2x values. So let's see what we get here. 0.655 plus 0.4983 divided by 100.6. And that is going to get us here. What's that going to get us? It's going to get us an x that's equal to 0.0115, we'll call it. And if we do the minus here, minus 0.65, I'm sorry, 0.655 minus 0.4983 divided by 100.6. And that's going to get us here, I think, 0.00155 or 6. We could go there, I suppose, in that particular case. Any questions on that so far? At this point, this is where we want to check which answer is good. In this case, we did not hit a negative, right? So here we did get 2 positive values. We go back to our ice table and just the equilibrium line for our H2, our I2, and our HI there. We have at equilibrium for H2 0.00623 minus x, 0.00414 minus x, and this obviously is actually a number here, huh? We had 0.0224 plus 2x. So in this case, obviously, if we took this number, for example, and we put it in there, 0.00623 minus 0.0115, I believe that should give you a negative number, yes, which is not so good. Yeah, so that is too big, which should hopefully mean this one is okay. So we're going to go with this one. So our concentration of H2 is going to be 0.00623 minus 0.00156. And that is going to get us here, 0.00623 minus 0.00156. 0.00467. Remember, this is molarity. This is a concentration. I2 will be 0.00414 minus X. So we're going to minus our number here. And that's going to get us 0.00414 minus 0.00156. That'll get us 0.00258 molar. And lastly, our HI in this particular case, actually, I'll go a little higher since it's a little low for people to see. When we go a little higher here, HI is going to be 0.0224 plus 2 times 0.00156. Remember, this is a plus. Again, a very common mistake sometimes people will do at this point, since they're used to like minusing x's, is to subtract at this point rather than add. So make sure that you do add. So 0.0224 plus 2 times 0.00156, or there we go. 0.0255 molar. So those should be, I hope, the equilibrium concentrations of everybody at this point. Any questions on that? We can obviously check our answer. I'm afraid to, but I'll give it a go. 0.0255 squared divided by 0.00467 divided by 0.00258, 53.96, which is 54. Feel better about it. There you go. Any questions on any of those steps? Again, obviously, I tried to show every single step along the way. You do need to show some type of work on a problem like this. It cannot, like I said before, just be the answer. And you need to do some factoring, some putting it together in the equilibrium expression, and something that makes me think you just didn't punch it into your calculator. You can punch it into your calculator, obviously, to check, I suppose, but you need to show the work. Any questions on it? All right, so clearly a little bit more involved of a quadratic than the one that we did previously. And as you work through this, you do want to just make sure that you don't lose zeros along the way and stuff like that. So, if you come across some that's a lot of zeros, maybe go scientific notation on those so you don't lose them, and put it back together correctly. Any questions on that? All right, then let's try another one here now that we're all warmed up, I suppose. There it is. Let's go back to it maybe. There it is. All right, it's Kp in this case. Is 4.31 times 10 to the minus 4. Calculate the pressures of everybody at equilibrium. If you started with 0.862 atmospheres of N2, 0.373 atmospheres of H2 in a vessel. Again, this is pressures. Kp works the exact same way as concentration. So just roll through like you're doing it with concentrations, but obviously they're pressures. So ice tables, all that stuff, all the same deal. All right, give it a go. Work on it for a bit, and we'll talk about it. Okay, so let's take a look to see how you're doing on this particular one here. So again, in this case, we are given a Kp, and we are given some pressures here. Like I said before, it works the same way as concentrations. You'll need to do an ice table, obviously, in this case. I think, as I also mentioned last time and today as well, again, if you are doing an ice table and it involves pressures, you should put it in atmospheres before it goes into the ice table. And if you need to convert it afterwards to some other unit, you should convert it afterwards. Again, even like I said previously, if they give it to you like in millimeters of mercury and they want the answer in millimeters of mercury, it should go into atmospheres before it goes into the table and to the ice table. So we'll do it the same way here. So maybe we'll borrow that. There it is. So we'll write our Kp expression in this case, which again is the same really as our Kc, except we're using pressures. So that would be the partial pressure. And again, we do need to still square it here of NH3 divided by the partial pressure of N2 times the partial pressure. And again, here we do need a cubit of H2. And that's going to equal our Kp value, which looks like it's 4.31 times 10 to the minus 4. Now that I wrote right into that ice table, I'll just rewrite the table down here, I think. There we go. All right, so in this case, we are going to put in our pressures in this case. So we'll start initially here with our N2, which is 0.862 atmospheres. And again, it doesn't matter their pressures. We're going to go 0.373 here. And once again, there's really no mention about NH3. So much like we did in previous tables, it is safe to assume that you pretty much have nothing going on over there on the product side. That once again also will tell us that this forward direction, right, should be happening. So we can safely assume for our change part, again, in this case, that reactants are going to be decreasing and products are going to be increasing. So I would say probably 90% of the time, 99% of the time, that's going to be the case. Minus is on the left, plus is on the right. But again, you could have a situation where perhaps it's going in the opposite direction. So in this case, it will be minus x for our change. It is a 3 here, so that is minus 3x. There is a 2 here, so that is plus on this side 2x. That's going to, as we bring it down here, I can get rid of the units here for simplicity's sake. So we don't have a lot of units in our way here as we're kind of doing a bunch of math. And we got our 2x. First off, any questions on the table here? So this, like normal, is going to go into our expression over here, and that's going to give us basically 2x, and that's going to be squared, divided by 0.862 minus x times 0.373 minus 3x. And again, we do need to cube that there, and that is going to equal 4.31 times 10 to the minus 4. At this point, that's some fun math, right? Nobody wants to do that math. So clearly the right answer is just to go to the next problem and skip this one, right? Forget this problem at all. So clearly we don't want to do that math. Even if we know how to do that math, we probably don't want to do that. So in this case, what we can do is perhaps think about a better way to do it for our purposes here. And one of the things that we could look at is the actual K value in this case. And when we look at the K value in this case, is that a large value or is that a small value? It is a small value, not a large value of K. And because that is a small value of K, that means when I reach equilibrium, should I mainly have reactants or products? We should mainly have reactants because of that. And that's important because of the change part here. If we are going to mainly still have reactants at equilibrium, are we going to have a tremendously big change occurring? No, not very much, right? And what we could do in this case, when you have a small equilibrium value constant, and remember, small is considered less than 1, basically, right? So anything kind of less than 1, we can make an assumption and we could assume that x is equal to 0. Now, the deal here is you cannot zero out all the x's because then you got nothing to solve for. So these are only the x's that you're going to subtract from a number or even add to a number. Yeah, so subtract or add. So in that case, it would be this x here we're going to zero out, and we're going to zero out this x as well. This one we cannot zero out. The reason we cannot zero it out is because it started at 0, which means anything that it makes is significant, right? But what's changing here on the reactant side is going to be a very small amount, which is not very significant, right? So if you got nothing, you get something, that's significant from where you started. But if you already have something, you lose a little, it may not be that big of a deal. So that again is why, besides the practical aspect of it, that if you zero out all the x's, you have nothing to solve for. But that's why we don't zero out that x, because it started at 0. So whatever it gets is kind of significant. So that's then going to make this maybe a lot better here. So that's going to give us 2x. We still need to square it. This will then give us on the bottom 0.862. And this will give us 0.373. By the way, we still need to cube it as well. So we still need to do that. And that's going to equal 4.31 times 10 to the minus 4. That looks like a lot better than what we were looking at previously here, right? So We're going to do that. So I'm going to kind of do the bottom there on the left and get some numbers here. So 0.373, we're going to cube it there. Got a button like that, maybe. 0.862. So if you kind of clean up this part of it, you're going to get 0.044734. We then going to really multiply that then to the other side, right? So we need to multiply that to the other side. And when I do that, I'm going to also take care of this, which is basically 4x squared. And that's going to equal, in this case, we'll multiply that to their side, 4.31. Make sure you use your exponent button. Too many zeros to read tonight. All right, we'll go with 1.928 times 10 to the minus 5. We then need to divide by 4. Yeah, we're going to divide 4 to the other side. And again, I'll go maybe, actually, get back here. There we go. I'll come up on top so you can see it, hopefully. So we're going to actually divide it by 4 first before I do that. We're going to get x squared is equal to 4.8200 times 10 to the minus 6. Obviously, at this point, we're going to do a little square root action on both sides. And that's going to give us an x value of looks like 0.00, we'll call it 220 in this case. Yeah. First off, any questions on that right there? All right, so in this case, yeah, I'm sorry. Say it one more time. So we're assuming x is equal to 0 in this case, based on the k value, and as long as the k value is considered a small value, which is typically considered anything less than 1. So anything with a negative exponent, usually you could try it. So it's a good question. When we do the assumption, though, you do have to check it to make sure it's okay. And so you can't just blindly do the assumption and hope that it works, because in some cases it may not work. In those cases, you put a sad face on it and then has to go back and do a little quadratic action or solve it some other way. But we do want to check it. So it's important when you do the assumption that you actually check that it's okay. So in this particular case, I'm just going to move my x value to here. So we basically had x is equal to 2.20 times 10, so minus 3, I think, if I'm not mistaken there. 1, 2, 3, yeah. And the way that we actually check it is we take the x value that we got and we divide it by whatever we were going to basically subtract it from. So, and this is how we're going to check it. And in this class, we're going to use what is commonly referred to as the 5% rule. And what that means is when you take your x value and you divide it by what you were going to subtract it from and times it by 100, if it's 5% or less, you're good to go. Yeah. If it's over 5%, then you put the sad face and go back and solve it. For our purposes, probably quadratic way. You have to go back and kind of solve it in that fashion. So we'll check this one here. So we'll take, for example, our x value there, 2.20 times 10 to the minus 3, which once again, I'll just put next to it our x value, divided by, for example, what we were going to subtract it from here in our first guy, 0.862. And times it by 100%. And in this case here, that's going to get you divided by 0.862 times it by 100. That's going to get you 0.25%. That gets you a happy face because that is definitely less than 5%. So you are good to go with the x value that you got. You don't have to go back and try to solve it some other way. Technically, you could do it for either of them. So that's 0.373. So 0.373. You also would times that x value by 3 because that's technically what you had going on there in the equilibrium line. So that's basically our equilibrium line there. And we would times it by 100%. And even if you did that guy there, you should be still in business. In my experience, if one of them checks out, you're pretty much good to go. They're all going to be all right in that case. So I wouldn't waste your time checking every single one. If you check one of them and it's good, I would say probably 99% of the time you're going to be in good shape. You don't need to check them all. So now that we checked it, which you should always do again when you do this assumption, once again, it may not work. It may be slightly above 5. It may be really above 5%. But if it is above 5%, you do need to go back, like I said before, and solve it some other way. And like I said, for us, that probably would mean you need to go back and solve it quadratic way would be what you would need to do. By the way, if you still love the quadratic and you want to solve it that way, you could do it without the assumption and just roll through that. If you love that math, you could do that as well. So again, like I said before, you could always roll with the quadratic if you want and solve whatever you need to do in pretty much most cases. So we still need to finish the problem here. So now that we have our x value here, we're going to put it back into our equilibrium line. And actually, so what's that? That is N2. So our N2 is equal to 0.6862 minus our x value there, which is 2.20 times 10 to the minus 3. Remember, these are pressures, so those are atmospheres we're looking at. So 0.862 minus 2.2 to the minus 3. That's going to get us something like 0.8, we'll round it, 60 atmospheres. For our H2, it's going to be 0.373 minus 3 times 2.20 times 10 to the minus 3. Again, these are atmospheres. So 0.373 minus 3 times 2.2 to the minus 3. That's going to get us 0.366 atmospheres. And lastly, here our NH3 is just 2x. So our NH3 is 2 times our x value. And once again, those are atmospheres. So 2 times 2.2 to the minus 3, 0.00440 atmospheres. And those would be our partial pressures. Again, we can also check it. We can put it back in. So in this case, I think we were squaring and dividing by 0.860 divided by 0.366 cubed, I think. And we get something like our 4.6 times 10 to the minus 4, which should be pretty close to our x value, our k value. Any questions on that one? Why did I not do the assumption on our previous 3 problems? Why did the quadratic? Why did I not do the assumption? Exactly. The k value in the very first one we did the other day was 7, which is considered large, which means you cannot do the assumption. The k value in the last 2 problems we did after that was 54.3, which clearly is large, which means you cannot do that. Again, because those k values are large, that means when you reach equilibrium, you should mainly have products, which means the change part is going to be fairly significant. And we could only try this again when we have a small k value. And you should always check it because it will not always work as we go through other chapters and this chapter as well, by the way, just so you know. Any questions on ice tables, how to solve them? We've done now 3 different ways: quadratic, perfect square, assumption. The only way we're not going to do in this class, like I might have mentioned before, is successive approximation, which if you're really crappy at it, will take you all day to do it. But basically, that's an idea where, just so you know, like I mentioned, you know that this x value has got to be less than that number. So you put in an x value there and you solve for like the x on top, the 2x there, and you keep putting in a value and solving for x until the number you put in and the one you get out is the same, which could take all day, all week if you're really crappy at it. So we will not do that, but you may see it in the book or something like that. Sometimes books and stuff will do successive approximation, but we're not going to do that. So those will be the 3 ways that you'll be required to be able to solve these type of problems. Like I said, quadratic, perfect square, or something like this where you could do an assumption. Any questions on any of that? Yeah. Yeah, so if at the end, and depending on this, and obviously with the previous one as well, depending on where you round, You might get a slightly different. It shouldn't be extremely different. It should just be slightly off. You would be okay. Yeah, again, as long as, for example, in this one, for the top one, you don't get something like 1.5 for the atmospheres or something like that. But if you got like 0.862 or A3 or A5 or like 0.858, you're probably good. You should be okay. Unless it's like extremely off and stuff like that. I would say typically when I do like usual, I try not to round too much, but in some of these cases, obviously with the quadratic, you probably don't want all those numbers. So I would just keep a couple extra numbers, and usually you'll probably be in good shape. And that's also why when you go back and check your K-value at the end, you're not going to get exactly the right number, right? Or the exact same number, because depending on how you round it and stuff like that. But again, it should definitely be in the ballpark. Other questions on that? All right, fun times. Fun times had by all. I like it. All right, then let us continue on here and talk about Le Chatelier's principle. And Le Chatelier's principle is gone. Oh, back there it is. Le Chatelier's principle is this idea of a system that's at equilibrium, and you have this system that's at equilibrium, and frankly, for lack of a scientific explanation, you screw it up. You do something to it that basically screws up the equilibrium. So remember that when we're at equilibrium, we have a reaction that has a forward direction and a reverse direction, that the rate of those things are equal to each other. So everybody's moving back and forth at the same rate. As we talked about, what that does is essentially just lock everybody into place in terms of their concentrations. If we're dealing with pressures, it locks it in terms of their pressures. Again, it doesn't mean that you'll have equal amounts of everybody on each side, but again, wherever they end up, when that reaches equilibrium, we'll lock them basically into place. So you could do something to that to kind of screw it up. And the nice thing about these type of reactions is, frankly, even if you go screw it up, it's going to try to self-fix itself. And it's going to fix itself and try to get itself back to equilibrium. And there's really three things that could happen. Two things really that helps it get there, and one thing doesn't do too much. But to get itself back to equilibrium, typically we talk about it shifting to the right. And when we're shifting to the right in an equation, we're talking about going towards the product side, right? So making more products will do that. Sometimes it will shift to the left. And obviously in a chemical equation on the left-hand side, those are your reactants. So we would head towards the reactant side. And sometimes you could do something to it and there actually will be no change. So that is a possible answer per se when you're asked what's going to happen to this system at equilibrium. So you have this system at equilibrium and you do something to it that messes it up. Those are sometimes referred to as adding a stress to the system. And there's a few things that you could do that will stress out a system that's at equilibrium. You could do something with concentration. You could do something with volume and pressure if you're dealing with gases. You could do something with temperature. And you could also add a catalyst to it. So these are common stresses that you could do to a system that's at equilibrium. And that system, again, like I said, will react in a way to try to reestablish the equilibrium. And again, try to reestablish that rate of the forward direction and the reverse direction, basically equaling each other again. So we're going to talk about each of these and sort of what happens in those situations. So we'll start with concentration. So really, in the case of concentration, there's kind of only two things that you can kind of do. You could either add more, and that means when you add more concentration, be it a reactant, be it a product, it will always cause the equilibrium to shift away from the side you added it to. So when we talk about sides, what are we really talking about? We're talking about the equation. We're talking about the reactants and the products. Obviously, if you have all this at equilibrium in a beaker, There really is no arrow, right? There's no left side, right side in the beaker or anything like that. You got everybody swimming around the pool together. But when we talk about shifting to the right, shifting to the left, that's in relationship to the equation for the reaction that you're looking at. So that is what we're talking about in this case. So when you add something and it goes away, AA is a good way to remember that, add away. And the opposite thing that you could do in terms of concentration is you could actually remove. And when you remove something, it will actually shift to the side you removed. Now, adding more concentration is pretty simple. You just go to the shelf, grab a bottle of reagent, and you dump it in your beaker or your flask or whatever you got your solution in, right? How do I remove something from a solution? Do I just reach in with my hand and grab stuff out? I hope not. That seems like a really bad idea, just so you know, for anybody listening to this. How do we remove something from an equilibrium? That's one way we absolutely could do it, right? We could add something, right, to say my solution here. And if we add something to my solution that then precipitates out as a solid, things that are solid are not included in the equilibrium, right? So that's essentially like reaching in and pulling out those ions. A reminder that ions are basically floating around in the solution part, right? So if you add something, solubility rules that will precipitate out something, one of those ions is now stuck in the solid state, not participating in the equilibrium. You just basically reached into that solution and took it out. Another way you could do it is, any ideas? Well, if you have an equilibrium that contains either OH minus or H plus, that's like a base and an acid. You could add either a acid or base depending on which one you got floating around. Because if you have OH minus, for example, floating around, and I add H plus to it, what do I make? Yeah, that looks like two H's and an O. That's water, right? And water is also not part of the equilibrium. So that would be like a way to remove hydroxide ions that are floating around the solution. Same thing if you had H plus solution ions floating around or H3O plus floating around. Add a little hydroxide to that. You make a little water. That is the way that you could remove some H plus ions from a solution. So sometimes you could add an acid or a base to a solution that contains either H plus or OH minus. You could pull those ions out as water. Will you visually see it? Probably not. You visually will not see that happening, other than maybe your equilibrium reaction will then maybe change color as a result of you removing the hydroxide or removing the H plus. But you can't maybe visually see sometimes you made water, but that's essentially, what's happening in that case. So those are two very common ways that we can obviously remove something from an equilibrium. We could add something to that solution that's going to react with those ions that are floating around and either take it out as a solid or take it out as part of water. Any questions on that there? All right. So for example, let's say we had a system at equilibrium. And this is advanced stick figures. They do have faces, just so you know there. Intro to stick figures, no faces. It's more complicated in this case. So we'll say the guy on the left here is our reactant side. The guy on the right there is our product side. And basically in this case, we're at equilibrium, we'll say. So we're at equilibrium position number one. And let's just say, for example, somebody else hops on to my little seesaw here. And if somebody hopped on there on the right-hand side, we would end up with something like this. And in this particular case, obviously, we screwed up the equilibrium there, right? Now, to fix this situation, I need more people on the left or the right-hand side here. Yeah, so we added people to the right. It's going to shift away from the right-hand side to the left-hand side to once again come back, hopefully, to equilibrium where everybody's enjoying the ride here, I suppose, right? He's semi-enjoying this ride, I think. And we're back to equilibrium position number two at this case. Now, if again we started with the same sort of deal here. Our guy on the left is our reactants. Guy on the right there is our products. And let's just say, for example, here we are obviously at equilibrium here. This guy decides, I've had enough. I'm just going to hop off. And he hops off. We're going to end up with this situation here. And now that guy doesn't look like he's having a good time. And we need to put more people on the left or the right in this case. Yeah, we actually need to put more people on the right, right? Towards the side we removed in this case, right? And that's going to then return us back to equilibrium. And our take-home message of the day is clearly don't get on this side of it, right? That seems like the bad side to be on. And we're back at equilibrium in this case, yeah? So what is really happening when we do this? When we add, for example, in my example here, more products, right? That is going to make the availability of our products a lot more than our reactants, right? And that's going to kick off the forward reaction or the reverse reaction. The reverse reaction in this case, right? Which is why I shifted away from it. Just like if I added more reactants, I would then have a greater availability of reactants than products, right? And that should cause the reaction to go in the forward direction, away from the reactants. Opposite is true over there where the guy hopped off. In the case where the guy hopped off of my products, what that essentially did was what? It actually made me have more reactants at that point than products, which means I can now have more reactants that's going to kick off the forward direction, right? Which is why it headed towards the products. Just like if I remove products, what's going to happen is I will now have a lot more reactants, right? Then I just did that one. I'll do the opposite there. If I removed reactants, I would then have a lot more products than reactants. That will kick off the reverse direction. It would head towards the reactants where I removed. So if you want to think about removing, you can think of it like a hole, like it makes a hole on that side. You got to fill it up, right? So it's got to go that way to kind of fill the hole. And when we add, it's always got to go away because, again, really what's happening is you're going to be kicking off the forward direction or the reverse direction, really based on kind of the availability of how much products or reactants you have as a result of what you did in that case. Any questions on that? Yeah. We used equilibrium in a practical sense in part A of the experiment, yeah, that we did the other day. In that experiment, we had an excess amount of iron, which means essentially what we did is we had a lot more reactants in that reaction that we're looking at in lab, for example. So we did this experiment, right? That we had a little iron 3. We'll do it today as well, right? We got a little bit of that action happening, maybe a little bit of this, right? Our goal is really to try to figure out, how much product we're going to make. So practically, if we didn't do the right amounts of these guys, maybe we wouldn't go to the right, or maybe we would, but not really force it to go almost all the way to the right on a one-way street. So by doing so, by really building up the amount of this, that's going to essentially cause this reaction to go in the forward direction. The result of that is because it's going in the forward direction, it's going to chew up all the other guy, right? Which is how we know that guy then becomes like a limiting reagent, right? And that's what's going to allow us, like we did there, to know if I want to know the concentration of this guy, it definitely is going to be based on this guy, right? Without having to worry about, doing some limiting reagent problem, which one's your limiting reagent. You basically force the issue on that, right? The nice thing about equilibrium as well is like you could actually go back and forth all day if you like. Yeah, you could push it one way, add some stuff and make the equilibrium go back the other way and back and forth by adding things, removing things. So again, in this situation, like in the experiment, our goal was to really be able to do a calibration curve based on having that product really produced and knowing that we didn't have just a little bit of the product, but we had a good amount of the product produced based on how much of the limiting reagent we had. So we were able to push it that way, and that helped us obviously do the experiment hopefully correctly. Other questions? All right. Now let's talk about another factor that affects equilibrium, and this usually involves gases. And when we talk about gases, that is volume and pressure. And they are oftentimes tied together. And I'm sure we remember from 200A, our friend Boyle, perhaps, I think was his name, how they pressure volume relationship, yeah? When the pressure goes up, what happens to the volume? does go down. And when the pressure goes down, the volume goes up, right? Smaller volume, everybody's in their way. They start banging around with each other. And then all of a sudden we have a lot of pressure happening, right? A lot bigger volume. They have a lot more space to fly around, not as many collisions. And we see the pressure start to drop. So when we think about equilibrium, and obviously this would have to involve gases for this to sort of take place usually. If we increase the pressure, we usually will have a much smaller volume. So if we think about what's happening in this case is in a small volume, that is going to give us a pretty big pressure or a good sized pressure. Again, because those gas molecules are pretty much trapped near each other, right? So that's going to definitely increase the collisions that's going to occur. So the change that's actually occurring if you shrink the volume is the pressure is going to start to go up. That's kind of the you screwed it up part of it. You just screwed up the pressure, it went up. So really what you want to do is kind of bring it back down. So clearly you can't change the volume in this case because you already did. So in that smaller volume, if I wanted to kind of bring the pressure back down from it skyrocketing, would I need more gas molecules in there or would I need less gas molecules? I would need less, right? So this would then shift to the side that has the least number of gas molecules. And now that's going to be dependent, obviously, on the equation you're looking at as to whether that's the left side or the right side. You can determine that pretty easy from the balance equation. You just look at left side, right side, add up all the coefficients for anybody that has a G, right? So anybody that has a G is a gas, so you just add up the coefficients and you can figure it out. Opposite sort of true here. If I lower the pressure as a result really of the volume increasing, what we have in this case now is a larger volume. So in this particular sort of aspect, we increase the volume. Really, the change that occurs as a result of that is we start to see the pressure decrease. So what we really want to do is, because the pressure is coming down, is kind of bring it back up. So in this case, in the larger volume, would I need more or less gas molecules to bring the pressure back up? I would need more gas molecules. So in this situation, it will shift to the side with more gas molecules. And again, with more gas molecules, that will kind of help the change that occurred where the pressure dropped. It'll kind of bring it back up a little bit to equilibrium. I personally, when I'm looking at these, always think about it in terms of volume. Small volume, less gas molecules. Large volume, more gas molecules. So small, small, large, large is a good way to remember it. And hopefully you remember Boyle's connection with that so you know what's happening with the pressure. So even if you're given a pressure, like the pressure going up or pressure going down, you could think about it in terms of volume, and that's a good way to remember it. Small volume, less; larger volume, more gas molecules. Now, what happens if you get a situation like this and they have the same gas molecules on either side of the equation? What happens? I think they call that in gambling a push, right? Nobody wins, right? So that is a no change situation. Yeah. So there really is no side that has more or less. So that is one place or one way that you actually could get a no change in this type of problem. You go, okay, well, we should go to more gas molecules or less gas molecules. When you go to the equation, they basically have the same number. So it will be a no change situation. Any questions on that there? All right, so let's just say I had my classic alphabet equation here, where B goes to, we'll go 4C. All right, so for each of these, tell me what's going to happen. Will it shift to the left? Will it shift to the right? Will we have no change? All right, let me write a few scenarios here. Give me a second before. We'll say let's add some more C. Let's remove B. Let's increase the volume. Let's add A. Let's increase the pressure. So in each of these cases, will the equilibrium shift to the right, to the left, or will there be no change? So take a moment and then we'll talk about it. 1, 2, 3, 4, and 5. Is a product that essentially means we're going to go away from where we added it. So it should shift to the left. Again, in this case, what's really happening is we now have more products than reactants. So it'll cause the reverse reaction in this case to occur, and it will shift away. How about if I remove B? It should go also to the left. B is a reactant. And again, however you want to think about it, you remove a reactant, you now have more products, going to cause the reverse reaction to occur. Or like I said before, you just made a big hole on the reactant side, you got to go fill it, right? So it's going to go towards that side and fill the hole. If I increase the volume, which way will it go? It will. Looks like I like left apparently in all the ones I chose here, but it will go to left. In that larger volume, that means really the pressure is going to start to drop, which means we then need to bring the pressure back up. So once again, remembering large volume, more gas molecules. That is 2 gas molecules and 3. That is a total of 5 on the left-hand side. That is a total of 4 gas molecules on the right-hand side, and that would shift that way. If I add A, it's going to go. It is going to go to the right. Here, A is a reactant. That's going to make more reactants and products, going to cause the forward direction to occur and head away from the reactant side to make products. Lastly, if I increase the pressure, where are we going to go? We are going to go to the right in this case. If I increase the pressure, I have a small volume. In a small volume, I need less gas molecules, which in this reaction is to the right. Any questions on any of those there? Okay. Next thing in terms of Le Chatelier's principle is temperature. Temperature works the same as concentration. That means that if you increase the temperature, it will shift away. And if you decrease the temperature, it will shift towards. The important part is to know which way the temperature is at. So, and that has to do with what type of reaction you have. As you may remember, there is an exothermic reaction, which they don't teach in 200A too much anymore. Exothermic is energy is released. Yeah. And because energy is released, we think of it, not 100% correct in all aspects, but we think of heat or energy as a product in an exothermic reaction, like it's being given off, basically. Most of the time, though, in terms of exothermic and endothermic in chemistry, we use delta H. Yes? Change in enthalpy. Also should be taught in the first semester. They don't do that anymore. They will soon. Change in enthalpy is delta H. And basically, if your delta H value is negative, that's going to mean that the reaction is exothermic. So I would say probably 99 times out of 100, that is how you will see whether or not the reaction is exothermic or endothermic is they will just simply give you the delta H value at the end of the equation. The number really doesn't matter. It's actually the sign. So if you see a negative delta H, you know it's exothermic. Endothermic, on the other hand, is when we have basically energy being absorbed. And in terms of Le Chatelier's principle, we usually think of heat and energy as a reactant in that case, like it is being absorbed by the reactants. And more often than not, our delta H or our change in enthalpy will be a positive value. So that means in this type of deal, if you have an exothermic reaction and you increase the temperature, that reaction will then shift to the left if you increase the temperature, because it is like adding a product. If you decide to put all your test tube on ice, that would be like removing the temperature. If you decrease the temperature in an exothermic reaction, it will shift to the right, and vice versa. In an endothermic reaction, if you increase the temperature, it will shift away towards the product side. And if you decrease the temperature, it will shift towards the reactant side like it is being removed. Yes, sir. I will say yes, I think. And actually, the Le Chatelier's principle one, which should be scheduled, I think, for next week. I think you do that here. It varies some semesters, but you can figure it out based on that. For example, if it's endothermic or exothermic, depending on what you do. So I think here we might still do it in that case, but you can definitely figure it out. Any questions on that there? So heat or energy is basically your product or reactant depending on the type of reaction. And again, we will sort of look at it the same way as concentration. Yes. Mhm. It will shift away from the product side because in an exothermic, heat and energy is considered like a product. Not really correct, but essentially what it does is it has, all that energy back in and allows the products to cause the reverse reaction to occur. All right, one thing before you wrap up for today, relax. You still have a lab to do. Yeah. Is a catalyst. Yeah. So a catalyst is not a reactant. It is not a product. And as you might have learned in kinetics, it does not get used up in a reaction. It is there in most cases to facilitate the reaction occurring faster. And it does so, as you might remember, by finding an alternative pathway to that reaction to occur, which is more efficient, ultimately lowering the activation energy, which is this hill that the reactants has to climb to get to the other side in terms of their products. And in terms of a catalyst in a reaction, a lot of times you'll see it written on top of a arrow, maybe like a metal, maybe H plus, like it's an acid catalyst. But they're there really just to facilitate the reaction occurring faster. In the case of Le Chatelier's principle, that is really the second way that you could hit a no change. It will not do anything in terms of the equilibrium. You'll just get there quicker. But the will not shift one way or the other, a catalyst. Also, sometimes if you add like a noble gas, they're chemically inert. They also will sometimes not affect equilibrium as well. And that gets you no change. Any questions on that?